The motivation for this talk is most of us, we do the production issues together, and the common question is usually, oh no, how should I scale this thing up? Or what number of threads should I use? Or the connection pool. Like what's actually the connection pool in PL, things like that, right? And especially last year, I think last year October, our scale became larger, and we're dealing with a lot of production issues. And if you check, majority of our production issues revolve around the DB is overloaded, and that leads to cascading effects. Or usually that, to be honest, 30% of that is usually that. Or the connection pool was not properly configured, right? We tend to get a lot of this type of issues a lot. And what triggered it was there was a day we were on the call and somebody asked, is there a mathematical formula that I can use to figure out the size of what was happening? I think it was we're having some sort of connection problems. We realized it was the operating system network stack, right? The networking, the outbound queue of the network carrier was getting filled up. And somebody asked, is there a formula I can use to kind of figure out what the size of the queue should be, right? To be able to get this. And I remember telling the person, oh, you can use Little's law to do that. And the person said, yeah, I know. The person told me that, oh, they know Little's law. But the question is, okay, how do we go from that law that we both know to how to size the queue? We both could not do that, right? We needed to then figure out a way to kind of arrive at the same. I'll still use queue theory to try to explain what we ended up doing. But what one jumped out to me was our idea, how we build performance or how we build performance system, right? And if you talk to some people, they will say, oh, I load test. I think after some issues, you start hearing things like, before you carry your service to production, you must do a load test, right? Or before you some other people would do things like they would deploy it and start scaling up gradually, right? So those are all methods where you kind of figure out how to answer the question, will my system scale, right? How many servers do I need? How many connection pools do I need? Things like that, right? Those are ways that people have been using to answer that, right? What this talk is about is another way, a mathematical model, right, that you can use to answer the same question, which is how many servers do I need? How large should my connection pool be? And this type of things, right? And that's what I want to try to communicate here in this talk. And the theory that kind of governs everything, right? And I think people say, or what I later found out was, it's like a hidden thing or maybe not hidden, it's ubiquitous, right? It's almost everywhere in terms of queuing theory in computing, right? The entire experience, like even as I'm talking to you, the way the packet is moving, the way the operating system is scheduling, everything is a queue, right? Everything in computing actually is a queue, right? If there's anything you're going to get out of this talk is, queues are ubiquitous. We all know what queues are. We deal with it daily. And even in computing world, it is actually everywhere. How the OS schedules, how the packets leave, your system and all of that, right? But we all know it intuitively, right? But we don't have a mathematical model to kind of link everything together. And that's what this talk is trying to that I want to do here, right? I want to try to do in less than 20 minutes. Queuing theory is the mathematical study of written inline skills, right? And we're all aware of this. Most of us Nigerians, we know of queue, but we know how to jump the queue, right? But it's something that we deal with daily, and there are models around it that you can use to predict how the system would behave. And the core intuition that I want us to live with is, or even for maybe I should try to describe. Maybe I should try to describe what a queue looks like, right? Like the kind of model that people use to kind of describe queue. So most most um most description of queue is you have arrival. I think some people draw it this way. You have a bunch of boxes to represent people queuing up. Then you have what you call a server, right? Processing or accepting different people in the queue. The rate at which people join the queue, um, it's usually called arrival rate. The rate at which the server processes each person at the distance. The way each server services each person and processes each request is called service rate. But there's an inverse relationship to it. That's called service time, right? We queue things on the queue. We have the server. The time the server takes to process each type item is called service time. The rate at which the server processes stuff is called service rate. And the intuition is, or the general intuition is, if you don't plan your queues well, if you don't plan your ability to service things on your queue well, the queue will build up. And that would lead to longer queues means that people will stay in the queue longer. And if you imagine that was your request, it means your request will take longer to process. It means your customer will be unhappy. And if you over provision the servers, it means you would have too much capacity and you would end up wasting resource, right? So queuing theory kind of helps us come up with a balance between how we're able to, or to mathematically model how we're able to come up with the balance between our processing ability. And processing can mean anything, right? It could mean processing a request, it could mean me talking to you, it could mean you answering people. But it is a model that can be used across board. One thing I also want to point out is modeling, or when you're trying to model the real world, it can be inaccurate as well, right? So the formulas I'm going to give, and if you're paying attention, it will jump out, right? The formulas I'm going to give, they are they are approximations of the real world. They will just point you, they will just give you intuition of what might be going on, but they are not, what's it called? They are not foolproof, right? Like I tried to describe before. So we have arrival process, right? Arrival to this queue, to your queue. Arrival is the rate at which it's the rate of the pattern at which people arrive, right, at your within your queue itself. So, for example, I'm looking for hospital, right? The way I think people go to hospital is a function of a lot. I remember in social studies they will teach us clean your environment, like avoid mosquito and things like that. That will reduce sickness, things like that. So, arrival is the rate at which people arrive at that queue. There are different arrival models, right? For engineering, the most common arrival model is called Python or Poisson arrival model, which the most important thing is you arrive at you arrive to the queue at a fixed rate, and each arrival is independent, right, of the previous one. And for most times that can be true, right? But at times it can be wrong, right? An example is, and we see that a lot here at Moniepoint, right? A service is not performing well, it's timing out. I think we call it thundering head, right? The thundering head is when the arrival itself is not independent, right? Meaning I try, it failed, then I keep trying and I keep trying and I keep trying, right? And that's another example of mathematical models. They don't actually model the real world, right? Because most of the time you model your arrival as an independent, like each arrival is independent of each other. But there are things that can happen, right? Or maybe you're trying to, maybe what we did, that time we were sponsoring Big Brother, right? People were coming to Moniepoint app more. So the arrival there has increased because of previous arrival or previous events that has happened. Another thing is the service process. Your arrival rate and your service process are kind of related, right? Yeah, essentially, what this means that is the rate at which the not rate, the rate at the if there's something for you to do, then your what's it called? Your the server, right? In the anatomy of that I tried to do here, right? So you have the queue, you have the server. Um, the rate at which things come in here, it affects the service rate, right? And the service time affects The service time also then affects the service rate. And that is why, for most of us, right, a lot of what we do is trying to minimize the service time, right, so that we can then have better service rate to kind of make things better. Then the other thing too is number of servers, right? And number of servers here is in this diagram here. You could have more than one, right, pulling from the queue. And if you notice, there's nothing I'll be saying that you guys that does not sound like you know, right? Because intuitively, queues are everywhere. There are things that we are all aware of. And I think usually the problem is the leap from the intuition we have about queues and putting that into some sort of mathematical model, and also building processes around when you're designing your system, modeling it with these things, right? I don't think there's anything I'll have mentioned that people are not already aware of. Like, just in case you're wondering why you guys are telling us what I already know, right? The other thing is queue discipline, right? So queue discipline means how do you take things out of the queue? Again, fellow Nigerians, right? Most of our queues don't have a strict queue discipline, right? So because you got there last, as long as you'll be the first person out, you'll be the last person that will be processed. But where they find a queuing system, and even at times we build systems too where here at Moniepoint, I've built systems where you want some sort of variable queuing system, right? First of all, you want the oldest thing in the queue to be treated first. But there are times where it makes sense, and we do that a lot here, where it makes sense where some guys have been waiting in the queue for so long. There's no point trying to process them first, right? Just jump to the new guys that are arriving, because those guys, what's it called? Those guys it will help create the perception of good performance, because the guys that are already in the queue for long, there's nothing you can do. So that, but queue discipline just says how you take things out of the queue and process them. The other thing is system capacity, which is the maximum number of things that can be allowed in the queue. Using Moniepoint as an example, ideally all our systems, we design them to have infinite capacity, right? What that means is that we want to process all requests that comes, right? But in reality, I want to talk about rate limiting, right? In reality, at times that can be a bad thing. And that's why you hear things like, rate limit your system, or do a load test, know how much you can handle. And the moment you hit that limit, stop accepting requests, right? But what business wants is probably an infinite system capacity. But these are all the properties of a queue, right? And all of these things have mathematical relationships that kind of link them together. And that is what I want to kind of try to show here. And hopefully, if we have a bit more time, move that to apply it in a practical sense, right? I don't know if anybody has taken any course in queue theory before, but everything I described is you see it written in this notation, right? And the most common thing you see is I think you see something along this line. You see something like M1, or I'm trying to write this MM1 or MMCK, right? That notation is called Kendall's notation, right? And what it just kind of tries to do is just how to put this together. Your arrival distribution, your service distribution, the number of servers. That is why you see MM1 often, right? Because the default is infinite retention. The population size, okay, sorry, I did not talk about that. Population size, in most cases, it's something I don't think you should worry about. Population size just means, for example, only a sick person will go and queue up at the doctor, right? So the maximum population size for the number of people that go and queue at a doctor is the number of people sick, right? So today, as also population size means that. And if you're able to estimate level of sickness in a country, you can estimate the maximum number of population. But it is just easier to reason about it as infinite. And that kind of helps. Yeah, in queue discipline, it can be the word queue implicitly carries FIFO as that stretch investor as a discipline. And I get a lot of trying to say the common distribution is Markovian exponential model and deterministic, right? So MM1 is quite common, right? The most important, I'm using the word important a lot, right? But the thing to be aware of with queuing is what we call utilization. And you would see this formula a lot in queuing now. So this thing here is called rho, it's called utilization, it's called queue utilization. and the lambda is arrival rate, mu is your service rate, and c is the number of servers, right? When what's it called? When number of servers is one, so most of the time you would see this formula a lot looking this way, right? Over mu, because most literature that you read just assume is one server, because it's simple to kind of use that model. And what it kind of, or the major thing I want to point out is that you want to make sure that your utilization is less than one, right? Meaning 100% utilization, you are less than 100% utilization. And what that kind of, and it's similar, I think we're talking about work-life balance and all of that stuff, right? What all of that just means is, if you're working all the time, if your utilization is close to one, or I think theoretically, once you're above 70 utilization, it becomes, I'll show you the graph later. You really are unable to keep up, right? So a stable queue is something, as long as the utilization is less than one, you would be able to cover the backlog. Any system that you build that utilization is greater than, to be honest, 70%, you're going to have a problem. And an intuition of how we already do this, right? Most of the time, the analysis. A way to kind of tell that is that you look at your CPU. Is your CPU utilization too high? What that means is that there is compute that is bogging your CPU down, and that means context switching will be hard. Anything will be hard. You perceive it as slowness, and what that slowness just means is what's it called? It just means that queues are building up, and that approach is common. You can use it across board, even as humans and stuff. So another that I was trying to communicate here is, when you're modeling your system, when you're looking at your system, you need to make sure that utilization is less than one. Anything above 70% utilization, that system is going to collapse. And it's going to collapse very, very quickly. It's not even, it will collapse in such a way where you have time to recover. And that's what, again, Moniepoint example. Anytime we're having issues, anytime we're dealing with all this thundering head where you are noticing you spin off one server, you spin off an additional node. Before you know it, the thing was dead. You spin off another node. It's because utilization. And it leads to almost this kind of yo-yo effect. At times, it takes hours to recover from. So I think I kind of slotting this idea to the classic MM1. These are now formulas to remember. So for example, your utilization is lambda over mu. The L is average customers or average entities in the system. If you notice, there is L and LQ, right? The difference is, normally in any queue, there are people waiting and there are people being serviced. That is what L is, right? So L kind of abstracts the total number of people in the system. LQ tells you the total number of people waiting in the queue itself. And WQ, which is the average wait time, right? And what this suggests also is the time I spent in the queue plus the time it took to service me for me to get out of the queue, right? That is what W is. Then WQ is the average time I spend in the queue till I get processed. And if you noticed, I'm talking about average a lot, right? And the reason, and if you've also spent time debugging stuff, you realize average is a very bad number to use to kind of do estimation. And this goes back to what I was saying about models. They are not infallible, right? They just give you an approximation of how systems behave. And queuing theory too is not an exception, right? What I'm trying to say is that these formulas here, they are supposed to let you know whether you are off by a very, pretty much to be a base for it to start your analysis, right? But it is not what's the word? You cannot, if you swear by it, you'll be wrong, right? So you cannot actually swear by it. So I kind of came up with a simple example here. A database does about 90 queries per second. That's the arrival rate. Each one is taking what's it called? An average of 10 milliseconds. Right. So pointing on that, the milliseconds here, the 10 milliseconds here is the service time. But the service rate is now 1 over that, right? Which is then 100 milliseconds, right? Then the utilization is 90%. What this means is that whatever this database is going to collapse, right? This database is not going to, it is bad, right? So a database that is doing 90 queries per second needs to spend way less than 10 milliseconds processing. Uh, so that's what I'm just trying to demonstrate here. All these formulas are difficult to remember, and they might not be they might not come to you. Like, you might not necessarily know your service rate, you might not necessarily know your other stuff, right? And that's where what this person Litu, he came up with this formula called Litu's the utilization what's it called? Universal law, right? And what it tries to say here is, in mathematical relations, I think if there's anything you take away, or if there's any formula that I should remember, is Newton's law. The reason is Newton's law. So I lied a bit here, right? Because this formula here is very focused on the distribution, right? It's expecting a Poisson distribution of our arrival rate, a what's it called? An exponential distribution of service rate, and a Q of 1. Ideally, if you've taken the Q theory course before, right, you need to depending on the arrival rate or service rate, you need to kind of derive the formula for all of this, right? What Little just kind of did was, you don't need to worry too much about the distribution. You don't need to worry too much about anything. This formula represents an approximation of a simpler model like Ohm's law and all this. You know the way Ohm's law, right? Like Ohm's law hides a lot of things from you, right? It's the same thing too, right? It's just an approximation of what your Q length will be if you know your arrival rate and if you know your. So the W here is not service rate, is the service time. And I think from an engineering point of view, this is a very easy formula to kind of remember and to try to use. For example, you have a service that is or you have a service that is processing something like maybe 90 requests per minute or something, right? Or per second. And each request is taking maybe 30 milliseconds. You can use that to determine what the queue length can be. And you can then use that to compute to kind of tune your Tomcat server network queue, your thread, and things like that. There's something I'm also kind of I don't think I'll talk about, but something I'm also not talking about here is that a computing system is a network of queues, right? For example, your operating system is a queue. Your operating system network stack is a queue. The scheduling is a queue, right? Everything is a queue, and they kind of then hand off to each other. So it is also almost very involved to use queue theory to model everything end to end. What you can do is I can model each one independently, and then you then use the worst performing one of them all to kind of use to say, this is the worst thing that can happen. And I think that's Amdahl's law that's what Amdahl's law is trying to say, right? Amdahl's law is trying to say your system is as best as your weakest, right? So if you understand the performance characteristic of your weakest, I use that to generalize as the biggest. I don't think I talked about it here. So this is what I was talking about in the utilization curve, which is called the hockey stick this thing, right? So if you are between, ideally, right, you should try to stay between less than 60 to 70% utilization. The moment you get above that, right, it balloons exponential, and it makes it very, very difficult to recover. Here, if you want for Moniepoint, that situation where we are struggling to scale up a service, and like, oh, let's add more nodes, oh, let's do this one. Oh, is it going down? Is it going up? Most of the time is a function of this utilization with it depends on the system that's being queued, right? Or of the part of the system that's being queued. Battles are building, utilization is high, and it just balance. So that my system feels fine. Yeah. The other thing I want to talk about is it's called the variance effect, right? And the reason I want to talk about that is it is possible for a system to have the same service rates, the same arrival rate and everything. But when there's a lot of variance in the service time, so let me use that. When there's a lot of variance in the service time, variance here means that we know variance now. I'm not sure the English to use again now. So like it's not the same. Different people are experiencing different service time, right? That would affect the overall waiting time of the queue, and it makes your system much more difficult to model. And this is why I'll use again. If you work for Moniepoint, this is why, or if you had ever worked together, this is why I usually would like to hear what P99, what P95 is, right? So now if I ask you, okay, what's the performance like? I might ask you, what's your P50 what's your P99, what's your median, what's your mean, what's your max. When I'm asking that, I'm trying to estimate what the variance of the system is, right? And that then lets me know, lets me then know when to kind of, what's the word? To throw, you got to put what you're saying into context, basically, about how do you use, how the different numbers they are seen, or how the, what's it called, how the key utilization, or how the performance you're looking at, you have to put it into context. Because what you try to do, you try to make sure that your P99 is close to your median as possible. Your P99 is close to your mean or max as possible. That would mean less variation, and things are much more consistent. Then process engineering, engineering applications, like I talked about connection pool, we use it for thread pool, we use it for load balancing, we use it for rate limiting as well. And I think I try to quickly talk about using it for connection pool, right? And because that's one thing that the reason I'm putting there, because it's one thing that I noticed we guess a lot. What's supposed to say that? Wait, it's one thing where we don't in my interaction with teams, there is no science to how they pick. What I'm trying to teach is there's a bit of science you can apply about how you pick things like my connection pool, the number of threads that you use, and even the number of Kafka partitions that you have. And I want to use connection pool as an example, right? And the way to model it is arrival rate is the number of connections you need per second. Service rate is the a query will take, right? But you're already seeing why this is a bit difficult too, right? Because depending on your system, right? If you're running different type of queries, then it then creates variability in your service rate, and it then makes it much more difficult to model, right? It also leads to slower wait time. The number of servers is the total number of connections that sorry, that's undone my head. C the total the pool size itself, that the maximum pool size that you want, and K is the maximum number of what's it called? The maximum number of people, like maximum number of people you want to keep waiting, right? To wait for a connection. And that is pretty much, you are saying how long I want to wait before I start saying cannot get connection in the pool. And the reason I'm also pointing out that we tend to design systems such a way where we make that K infinite, right? The important thing here is the K, meaning your timeouts, the timeout that people should wait for, how long. There are two ways to model it. You create a large timeout. If you create a large timeout for how long people can wait to get a connection, you're essentially saying, I am building an infinite capacity queue. But if you have a short timeout, you are then saying, I want a fixed amount of people to wait. And the theory is try to keep your utilization of the connection pool less than 70%, and just let things break, right? Well, when I say break here, meaning fail fast, so that it's not I think I kind of put it unbounded waiting time, large queue size, high overload, and requests can pile up invisibly, and latency skyrocket, and it can become a problem. That's all I have for you today. Any questions?